Okay, hello everybody. I am back. I am still outside. I'm still wearing a Twins hat, even though they haven't won a playoff game in years. But anyways, what I'm going to talk about today is a follow-up of what I talked about in the previous lecture on basically using R to account for variance in Y based on predictions made on the basis of X. So what we're going to do here is basically going to run a linear regression in R using data we've seen before, and then try to figure out what the numbers are telling us in the output of the R command. So if you want to follow along, if you're at home doing this sort of on your own, for whatever reason, you can click on this interpreting linear regression results down here link, and it'll show you this. So I started a new R session, so I'm going to have to load my monowords database back in here. And once again, I'm going to grab, actually before I do that, I'm going to attach the monowords in case I want to use those variable names again, and now I'm going to just cut out that first set of 5 data points that we've seen before. Maybe I'll expand this a bit so you can see everything in a nice orderly fashion. So there's our data, and we're going to run a very basic linear regression analysis. And so I have a question here, which is not really the question that I've asked yet in the lecture, but we'll get to in the next one. I'm going to do the example before I tell you what it means, and we'll kind of walk through basically everything in a bit of reverse order, but just to make sure you're understanding why this is relevant or practical for our purposes, I want to do this part first. So this question asks, how can we calculate whether the parameters of the best fit regression line are significant? Which is not honestly a question that people ask a whole lot, that I've seen people ask a whole lot when they do social sciences research or linguistics research, but it is one you can ask. And R will tell you the answer any time you run a linear regression analysis. Right, let's start out by just doing the analysis that I've been talking about. So we're just going to only look at the first 5 data points here, and we're going to see how familiarity depends on frequency, and we've seen these numbers enough now that I don't think I need to belabor them again, but this is our familiarity data and this is our frequency data. We've seen this before as well, like the linear model here. The notation is, if you use the tilde, that just says, well, this variable depends on this variable, or so I'm going to assume that in the model that I'm running here, which is a linear model, or LM. What we haven't done before is run this summary command. So this is going to summarize basically all the relevant statistical analysis results of the linear model. So I'm going to hit return here, and boom, I get all this stuff. And I'll expand it a little bit so you can see where I started from. Yeah, so we're there. Okay, so this is the formula I'm using, right, that we've seen already. It's got this stuff called residuals, which is a fancy term for errors. So these are kind of like the errors we get for each prediction, for each of the 5 words in our data set. And now maybe you can see why I'm only looking at 5 words here, because if I looked at 4,000 whatever words, this information would get overwhelming in a hurry. But it's not, right? So some of these, it's making better predictions than others. And if it's making a good prediction, it should be close to 0, right? So it's making a really good prediction here for plug. It's not making such a good of a prediction here for number 2, whore. We've talked about that one before. But then it's also giving me this other stuff here. So these coefficient numbers. And these look like something we've talked about before, right? So we've got intercept here, which is going to turn out to be the intercept. And this is our estimated intercept right there. And then it's got this variable name here, first 5 frequency, and it's got an estimate for that as well. So what the heck does that mean? Well, if we go back to our commands worksheet, we can calculate the slope, or what's supposed to be the slope of this equation based on all this math that we talked about before. So let's see if I can find it. Yeah, so slope, and I've got a plus here, so we get slope equals R times standard deviation of Y divided by the standard deviation of X. So here's R, right there, our correlation coefficient for the 2 variables. Here's a standard deviation of Y. Here's the standard deviation of X. So if I hit return here, I should get the slope. And the slope is 1.081669. Up here, it's listed as 1.0817, so there's a bit of rounding off here, but it's the same thing. basically what this so-called estimate is telling me in this table of numbers is that this is the slope. And if I go back to my equation for the intercept, which is more complicated, as we've talked about before in the lecture, and I'll zip this up a little bit so you can see it. Maybe you can still see it. But it's supposed to be the mean of y minus the slope times the mean of x. So we've got the mean of y, and I'm making this all explicit so it looks like a mess here. And then that's the slope equation right there, as long as I'm including this division by the x-axis. Sorry, x variable. That wasn't a street cleaner. That was just a guy with an old engine. And then I'm multiplying it by the mean of x. So if we go, I don't want to get lost here too much with my stupid jokes, but r times standard deviation of y times the mean of x. We can see that here, this middle line. The guy just turned around and just wanted to come back again. You're famous now, sir. You've done your job. Anyways, here's the mean of y. Blah, 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 blah. I hit return. I get negative 1.335, and that is my estimate of the slope or intercept right here. So these are my linear equations for this, my parameters for this linear equation for the best fit line. Okay, so that's what that is telling me. There's also some other stuff here in this table. What the heck does that mean? There's also some other stuff down here, like what the heck does this stuff mean? So what I want to kind of answer first is this question I put out at the beginning of this little web page, like how can we calculate whether the parameters of the best fit regression line are significant or not? And that's actually going to be answered by this column, which is it's PR and then this notation greater than T. This is probability. It's a p-value is what it's telling you. So this is the p-value for some sort of hypothesis about the intercept, and this is a p-value about some sort of hypothesis about the slope. So first I want to show you like where do these p-values come from, and I've got the math for that in here. So we'll start off with, actually the only one we're going to do is the p-value for the slope, because the intercept is kind of boring in this example. But what I'm going to do here first of all is go back to these this sort of predict command. So this is basically going to tell me what are the predicted values of familiarity based on what I know about frequency. So I'm going to split those all into this vector called predictions, and they look like this. And we've seen this before, so I'm not going to kind of belabor it again. Yeah, but basically they're going to hopefully be higher for higher values to begin with, like stress is supposed to be 5.6. We're predicting 5.7. And as we see here, the difference between those is negative 0.1. So that's our residual error. Okay, so we can also calculate those errors explicitly, since R is conveniently designed to do so. So we'll have errors equal to predictions minus the observations. This is y hat, and this is just y. Or maybe you could say this is y hat sub I, all the y hat sub i's, and this is all the y sub i's. Motorcycle. Anyways, if we look at these errors, we see what we saw before. It's listed in a different sort of polarity because the subtraction is taking place in a different direction. But our error for that third term is 0.1 in this case. These should all match up with what we see here in what's called the residual errors up there. Okay, so nothing new there. We just have it in a vector that we can play around with. And I'll show you something fun as long as we're here. So we just figured out what are the predictions and what are the errors. Well, why don't we take a look at the covariance of those two vectors. And it tells me when I do that I have 1.102634 E negative 16. And so some of you have seen this notation and are like, okay, yeah, sure. And then other of you have seen this notation and are like, what the heck is this? E is not a number, or maybe it is, but usually negatives are not in the middle of numbers. So what's going on? Basically, this is R's way of representing a very, very small number using what's called scientific notation. So what it's saying is that basically this 1 at the beginning of the number is supposed to be the 16th number after the decimal point, and everything before that one is a 0. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 102, 6, 3, 4. And the only reason R is not spitting it out like this is because that's a waste of space. Because whenever you have a number that's this small, it's basically 0. And in fact, I don't know if I'd have that much of a problem with R just saying 0 here, because it would cause less confusion. But this is the number it's trying to represent. It's just trying to save space by using this sort of e to the negative 16 notation. Yeah, whatever. So I got that right, which is convenient. We can also do the correlation coefficient of these two guys, which is also extremely small. But the main moral of the story is that there's no correlation between the predictions and the errors. This number is basically 0. So this is a case where you get a correlation of 0 between two different data sets. And actually, I was thinking the other day of another way we kind of come up with that sort of scenario. So let's create two samples of random numbers. One we'll call X, and the other we'll call Y. And if these are truly randomly selected, and I don't know exactly how R selects things random, but if they're truly randomly selected, there should be no correlation between them because they have nothing to do with each other. So let's see what we get. Well, we got a correlation of negative 0.12, so there's a little bit going on there. We can maybe plot the two and see what happens. So this is what it looks like when you have basically no real correlation. I don't know if this will help you in that guess the correlation game, but this is what it looks like when you have a correlation about negative 1 or negative 0.1, sorry. Let's do that again. Maybe we can do better. I was playing around with it before, and yeah, there's one. This is basically 0 in terms of correlation, and again, it's just random numbers. So yeah, that's what that correlation looks like, and it probably doesn't look that much different from what we saw before because, you know, whatever. It's hard to get any sort of meaningful information here. And actually, we could try doing this, I guess. Yeah. Let's plot a best fit line. What do we get? Look at that. It's just a horizontal line. So there's a slope of 0, basically, when you get that. Because if R is 0, then your slope's going to be 0, right? So this is just telling me that it can't find anything meaningful going on in that analysis. I'm going to keep those there. Maybe I'll come back to that again in its own linear regression analysis. But basically, well, let's do it now. Why not? So summary, LM of Y as it depends on X. And we get this. So again, this is going to be basically my R value. And I'm getting similar numbers here. This is my estimate of the intercept. It's 50. And my slope is that. And it doesn't tell me all the different residuals here because I have 100 numbers. It tells me like a 5-number summary of them, but you can kind of figure out what that means. I'm not going to dwell on this a lot, but I'll come back to it in a second. I'll probably go back to that original model we had because that's the one I want to focus on. So we figured out what this means. We figured out what that means. We figured out what the world looks like when we have an R of 0. What we want to do here, instead of all that fun stuff, is I want to calculate the sum of the squared deviations of the residual errors, which is this. So how much variance do we have in this, basically? Put that in its own little vector. We're going to sum up all those errors squared. We get a value of 1.1, which doesn't mean a whole lot to us. And what I want to do here is calculate the variance for that error. And we'll do that by creating another vector called var errors. And we're going to divide this sum of squared errors by 3. And I have this question here, which, like, teachers often say there are no stupid questions, but I'm looking at this question and I'm thinking this is a stupid question. Not because it's a bad one to ask, but because I can't remember the answer. But we're dividing by 3. Normally in cases like this, where we have 5 data points, we'd say our degrees of freedom. Normally variance is sum of squares, squared deviations divided by degrees of freedom. So this is the degrees of freedom here in some case. But we're not dividing by 4. Normally we'd say our n is 5. We subtract 1 from that, we get 4. We're dividing by 3 here because I think we have to take both the means of x and y into account. So it's degrees of freedom minus 2. And like I said, I'm not 100% positive about that answer, but I think that's where that's coming from. And again, though, we're dealing with situations in stats and in linear regression where we're not 100% about some of the situations, right? That's where this stuff comes in handy. Anyways, what is my variance in errors? It's 0.3670796. Okay, great. Why do we care about that? Well, what we want to do is divide that variance by the sum of squared deviations in the independent variable frequency. Let's square and sum those deviations first. This part I understand and can remember. So this is my deviations for x. I'm not going to look at that value, but I'll sum the squares of those deviations and get SSX, which is 3.68, so on and so forth. The standard error is now going to be the square root of the error variance divided by the sum of square deviations of x. This is stuff I'll walk through in the next. This is math I'll walk through in the next lecture. But basically, when we calculate this value, you might be able to see that it's the exact same value as this standard error here. So, yeah, generally speaking, when you run a statistical analysis in R, it's going to be spitting out a lot of numbers like this at you because it's kind of be looking at things from the default of running a null hypothesis significance test. And in most cases from here on out, I'm not going to explain to you where these numbers come from, but I'm just going to explain to you in this one case kind of how to walk through the interpretation of this model. So we have this estimate, which we have from our best fit line analysis, and I've walked you through all the math for that. We'll talk a little bit about where this math comes from next time. But basically what it's going to do is say, well, I'm making this estimate for what the slope is for this line. But even with that estimate, with that sort of like best fit approach, there's some error in that estimate. And using this math here, we can estimate what that error is, sort of like what we were estimating the error of the mean when we were talking about like running t-tests. For comparing the means of two samples or looking at how the mean differs from a specific value like 0 or something like that. Either way, there's some uncertainty in this estimate. And there's a question, though, about whether it's so uncertain that we can't tell if it's different from 0 or not. So that's basically the question we're trying to answer when we ask, is the slope of the regression equation significant in some sense? Is there a significantly meaningful connection between these two variables such that I can predict one from the other? So we've been through this before, but if I want to put these two quantities into variables, I have to call them slope and standard error of slope. They're the exact same values we saw up here in the table. And to calculate what comes next in the table, this t value, I divide the estimate by the standard error. And that gives me something I'm going to call t-slope. And if I take a look at that, it's going to be equal to 3.428189, or 3.428. Okay, why do we care? Basically, again, what R is trying to do by just running this analysis is trying to figure out whether this number for the slope of the equation is significantly different from 0. Because if we have a slope of 0 like this, that means there's no relationship between the two variables. So is my slope far enough away from that to say, well, there's something meaningful going on here? There's some sort of connection between x and y such that I can predict y from x. And at the end of the day, it comes up with this p-value based on this t-value. Not only on this t-value, but also based on this number of degrees of freedom. 3. If you remember with the t distributions, they varied a little bit depending on how many degrees of freedom you had. So we have a t statistic of 3.428, and then we have 3 degrees of freedom. And then based on those two parameters, we can calculate that the p-value for the slope is 0.0416. That is less than 0.05, which is normally our alpha criterion. And because of that, R puts a little star there. It puts a little asterisk right next to it. That means this is significant. This slope is significantly different from 0. So we have a connection between our two variables. And you might notice as well here, sorry, it's chilly out, but there's different notations that R uses for sort of different levels of P. Like sometimes you might, if you're being generous, set your alpha criterion to be just 0.1, and in that case you would get a little period, a little dot next to this sort of p-value. If it's not even close to that, if it's above 0.1, you get nothing, like in this p-value, which is 0.46. If it's 0.01, if it's sort of really significant, you get 2 stars, and if it's 0.001, you get 3 stars, so on and so forth. Right now, we're just under the criterion. We're at 0.0416. We can still call it significant because it is, but that means that slope is different from 0. It's, in this case, positive, more positive than 0. Yeah, I'm going to show you here another way to get the same t-value, which is to get the correlation between these two guys, which is 0.892, so that's pretty high. And then I'm going to use this equation, which is that r value divided by this fraction here, the square root of 1 minus r squared, which, if you watched the last lecture, you know is the coefficient of alienation. So what do you know? Here it is again. Alienation, it's hard to get away from. And then here's our degrees of freedom on the bottom. And we'll call that t-slope 2, and it turns out that's the slope of this equation. Or sorry, that's the t-value for the slope here of this equation. We can do the same sort of null hypothesis analysis to say, well, that's significant as well. As opposed to all this stuff we did before, you might find this to be an easier way to calculate the slope, the t-value for the slope. I don't know. It's the same way to get to the same spot. And I've said here in this little commands webpage what I just said before, that we're looking at whether or not the slope is different from 0. There's also a way to do this for the intercept. And the first time I taught this class, I had a student who really wanted to know what all that meant. So I looked up all the equations for it, and it works in a similar fashion. It's making an estimate for the intercept. There's a way to calculate the standard error for that estimate, and on the basis of that, you get this t-value. It's basically the estimate divided by the standard error, and then on the basis of this t-value and these degrees of freedom, you get a p-value. The p-value in this case would be the probability that this intercept is different from 0, which, yeah, in this case it isn't. It's pretty close here, but the bigger picture question is, why would you care? In this case, we don't really care if the intercept is different from 0, and it's hard to come up with a case where you might. You can look at what we did up here with these just 2 randomly generated variables. The intercept here is estimated to be 50, because if you're just randomly generating numbers from 1 to 100, your average number is going to be somewhere around 50, right? So that makes sense. And if we look at the plot too, right, it's kind of centered around 50 in both dimensions, because why not? So that's different from 0. But again, who cares? What we normally care about is whether there's a connection between the two variables. And here that estimate is very small. It's almost 0. And then you wind up, of course, with a p-value, or like a t-value is going to be very small too. It's going to be close to 0. And the p-value, therefore, which tells you how likely it is that your slope is different from 0, that's going to be very big. So that's not going to beat this sort of criterion, no matter whether you're using stars or periods or whatever. So this is not significantly different from 0. There's no connection between these two variables. That's what you'd get for a negative result in your linear regression. Yeah, let's see. On the bottom of this, I'll do it one more time. On the bottom of this table, we have some other numbers. So these residual standard errors, R squared and F statistic, so on and so forth. Where do we get that from? So if we look at the square root of the sum of squares of our errors divided by the degrees of freedom, we get this 0.6058 blah blah blah, which turns out to be this residual standard error. That's just where it's coming from. So the sum of squares of the errors divided by the degrees of freedom. This looks a little bit like a calculation for variance, right? Because we have sum of squares divided by degrees of freedom. And then we're also taking the square root of it, so it makes it look a little bit more like standard deviation of the errors. So you can kind of think of that as what this is telling you right here. How much does it matter? Not a whole lot right now, but we'll get back to it again. If we want to look at the R squared value, that's simple to calculate. We can do that two ways. Either sort of our nice correlation command in R, or just using the variable R that we stored before. It's 0.7966, which is right here. There's an adjusted value of it, which I'm not going to talk about, but that's where R squared comes from. So this is how much of the variance we're able to account for in familiarity based on frequency, and it's about 80%, which is pretty good. But like we said, there's a significantly meaningful relationship between the two. We know that already, so this should be a pretty high number, in theory. We can also look at it this way by talking about the variance in predictions divided by the variance in the y variable to begin with. Down here, look, that's exactly what we saw before. It's how much variance you can account for. It's about 80%, 79.66, so on and so forth. That's what R squared is equal to. How much variance can you account for divided by how much variance there is. And lastly, but not leastly, I'm going to say that we can also calculate or figure out how to get to this F statistic down on the bottom. And that is going to be the variance in our predictions divided by the variance in our errors divided by 3. That will give me 11.75. This is a ratio. And the only time we've kind of played around with ratios of variances before is when we were looking at that F test a while back. But this is going to give us an F statistic. It's also going to have 2 degrees of freedom, and there's going to be a p-value associated with it. The cool thing about this, as I mentioned down here, is that for some weird reason, this F ratio, which we know comes from this, is the same thing as our t-value squared. That's weird. And in fact, when we go back and look at this, this has a p-value of 0.0415. It's basically the same thing as the p-value for our t statistic for the slope. There's some sort of weird connection there. So that is cool, but we're not going to answer or resolve that mystery right now. I'll just say that I'm going to say a lot more about this, when I start talking about ANOVAs, which I hopefully start doing by Thursday of next week. But this is what the results of this linear regression analysis mean, or at least how to interpret it. Normally when you run this for yourself, if you're doing your own analysis, you'd focus on this line here because it's kind of the most important question you're asking. But this other stuff gives you some useful information as well. And as we move forward, we're going to be focusing mostly on what this tells us, because we can expand that beyond just a variable between one connection, or a connection between one variable and another. I've babbled through this enough by now, and I'm going to stop at a moment when there's very little traffic and a lot of sunshine. Okay, I hope your day is going just as well.